All right, buckle up, because today's deep dive takes us into the world of Diophantine equations.
Oh, yeah.
Sounds kind of niche, right?
It kind of is.
But trust me, these equations are a gateway to some seriously mind-bending math.
They might seem simple at first glance, but they've puzzled mathematicians for centuries.
Exactly. We're diving into excerpts from the Wikipedia article on this very topic,
Okay.
and I'm already fascinated.
Yeah.
So what makes an equation Diophantine?
It's all about the solutions we're looking for.
Okay.
With Diophantine equations, we only care about whole number solutions, integers as they're called in the math world.
Okay, so no fractions or decimals allowed.
That's right.
It's like we're suddenly playing by stricter rules.
Precisely. And that's where things get interesting.
Okay.
You see, these equations pop up in all sorts of places, but restricting ourselves to just whole number solutions can be surprisingly tricky.
Now that you mention it, it does sound counterintuitive.
Yeah.
Why make things harder on ourselves?
Right.
What's the payoff here?
Because it unlocks a whole world of fascinating puzzles and insights.
Okay.
Take the Pythagorean theorem, for example.
Yeah.
That's a Diophantine equation in disguise.
Wait, the Pythagorean theorem?
Yeah.
You mean A plus B except C?
That's the one.
The one we all struggled to remember in high school geometry.
That's the one. It tells us that in a right-angled triangle, the square of the hypotenuse, that's the CK, equals the sum of the squares of the other two sides, A and B.
Right.
But here's the Diophantine part.
Okay.
This theorem only works if the lengths of those sides, A, B, and C, are all whole numbers.
Ah, so it's not just about the equation itself, it's about the specific types of numbers that make it tick.
Right.
Suddenly, geometry class is feeling a lot more intriguing.
It's a prime example of how a seemingly simple concept can lead to some seriously deep mathematical waters.
Yeah.
And trust me, we're just dipping our toes in.
Okay, you've definitely piqued my curiosity. And we're back, diving deeper into the fascinating world of Diophantine equations. So we've established that these equations are all about those whole number solutions.
Right.
But where did this whole idea come from?
Well, we owe the name and much of the early exploration in this area to a brilliant mind from ancient Alexandria, Diophantus.
Diophantus.
Yeah.
That name rings a bell.
Yeah.
Didn't he do some groundbreaking work with algebra?
You got it. Diophantus of Alexandria, often called the father of algebra,
Right.
was a true pioneer.
Okay.
Imagine a time when math was basically all words,
Yeah.
no symbols for equations.
Wow.
Diophantus started changing the game by using symbols in algebra.
I can only imagine what a difference that must have made.
Oh, yeah.
Algebra was tough enough as it was.
Right.
Having to write everything out in words would have been a nightmare.
Precisely. And his work on these equations, where he specifically sought out integer solutions, was truly revolutionary.
Okay.
He even wrote a whole book on the subject, Arithmeticum.
Oh, okay.
Sadly, only parts of it survive. But those surviving parts have provided mathematicians with puzzles and inspiration for centuries.
It's incredible to think about
Yeah.
these ancient mathematical mysteries echoing down through the ages.
I know. It's really cool.
So what kind of legacy did Diophantus's work leave?
Okay.
What are some of the big Diophantine puzzles that emerged?
Well, some of the most famous and challenging problems in mathematics stem directly from Diophantine equations.
Okay.
Take Fermat's last theorem, for example.
Okay.
A problem that puzzled mathematicians for over 350 years.
Wait, Fermat's last theorem, that rings a bell.
Yeah.
Isn't that the one about how you can't make a right triangle with whole number sides if the power is greater than 2?
Exactly. It sounds so simple when you put it like that.
Right.
The equation is x plus u say.
Okay.
Fermat claimed that this equation has no solutions in whole numbers for x, y, and z when n is any whole number bigger than 2.
Okay.
Seems like a bold claim, right?
It does, and to think it took centuries for mathematicians to actually prove it.
Yeah.
Why was this problem so captivating to mathematicians?
Fermat himself is part of the intrigue.
Oh, okay.
He famously jotted down this claim in the margin of his copy of Diophantus's Arithmetica, saying he had a marvelous proof, but that the margin was too small to contain it.
Oh, come on.
Talk about a
No.
tease.
Classic mathematician move.
Right.
Leave a cryptic note for future generations to puzzle over.
Exactly.
That's amazing. Are there any other brain-bending examples that came out of this Diophantine world?
Oh, absolutely.
Okay.
There's the Erdős-Strauss conjecture.
Okay.
Now, this one might not even look like a typical polynomial equation at first glance.
Okay.
It states that for every positive integer n greater than or equal to 2, you can always find positive integers x, y, and z that satisfy this unusual equation. 4n equals 1x plus 1y plus 1z.
Okay. I'll admit that one's beyond my mental math skills at the moment.
Right.
But it sounds like these Diophantine problems really capture the imagination, don't they?
Oh, they do.
What's fascinating is how the scope of these problems evolved over time.
Yeah. You're right.
Okay.
In the 17th and 18th centuries, brilliant minds like Fermat and Euler were grappling with individual equations, often spending years trying to unravel their secrets.
It's incredible to think of those mathematical giants dedicating so much time and energy to these seemingly simple equations.
It really speaks to the allure of these problems.
Right.
But then in 1900, David Hilbert, a prominent mathematician of his time, changed the game.
Okay.
As part of his famous 23 problems for mathematicians to tackle in the 20th century,
Yeah.
Hilbert posed his 10th problem.
Okay.
He asked if there was some sort of general method, an algorithm,
Okay.
to determine whether any Diophantine equation has a solution.
So instead of trying to solve each equation individually,
Right.
he was looking for a universal Diophantine equation solver.
Exactly.
What a challenge. Did they find it?
Well, that's where it gets even more interesting.
Okay.
It took until the 1970s,
Wow. Okay.
but mathematicians building on decades of work
Yeah.
proved that no such algorithm exists.
So there is no way to determine...
There's no one-size-fits-all method for solving Diophantine equations.
That's amazing.
Yeah.
So even though these equations seem like simple puzzles at first,
Right.
they touch upon some really deep mathematical truths.
They do.
It's like we've gone from ancient Alexandria to the 20th century and encountered some mind-blowing concepts along the way.
Exactly.
But it strikes me that we've mostly talked about these equations in terms of algebra, right?
Yeah, you're right.
Okay.
And that's only part of the story.
Okay.
There's a whole field called Diophantine geometry that explores the fascinating connection between these equations and geometric shapes like curves and surfaces.
Well, okay, hold on. Geometry.
Yeah.
Shapes and graphs.
Uh-huh.
How do those fit in with these whole number equations?
Yeah.
This is where we're really going to dive deep, isn't it?
It's where things get really interesting.
Okay.
Imagine you have a graph, right?
Yeah.
And you've got a curve on that graph.
Okay.
Some of the points on that curve might have coordinates that are whole numbers.
Yeah, right.
Those special points. Those are essentially the solutions to a Diophantine equation.
So instead of just finding numbers that make an equation true,
Right.
we're looking for points that land perfectly on a curve,
Yeah.
but only the ones with whole number coordinates.
Precisely.
Okay.
And the type of equation, whether it's linear or quadratic, for instance,
Yeah.
dictates what kind of curve you get.
Right.
A linear equation might correspond to points on a straight line, while a quadratic equation might relate to a parabola.
Okay. I think I'm starting to see the connection here.
Okay.
But what's the advantage of thinking about these equations geometrically?
Yeah.
What new insights does that give us?
For one thing, it gives us another way to understand these equations.
Okay.
Even if we can't easily find all the whole number solutions,
Right.
visualizing the problem geometrically can provide a whole new level of insight.
It's like we're adding another dimension to the problem.
Exactly.
We're not just dealing with numbers anymore. We're dealing with shapes and spaces.
Right. Exactly. And sometimes when you shift your perspective, the solution becomes clearer.
Yeah, I can see that.
It's like looking at a puzzle from a different angle.
This is blowing my mind. We've got ancient mysteries, unsolvable problems, equations, shapes. It's all connected.
It really is fascinating, isn't it?
It is. But before we get totally lost in the world of Diophantine geometry,
Right.
let's talk about a specific type of Diophantine equation that sounds a bit less intimidating. Linear Diophantine equations.
Sounds like a plan. Linear Diophantine equations are a great place to explore some of the techniques used to solve these intriguing problems.
So what makes a Diophantine equation linear?
Remember how we said that Diophantine equations generally involve whole number solutions?
Yeah.
Well, in a linear Diophantine equation, the unknowns, your x's and y's, are only multiplied by constants and added together.
Okay.
No fancy exponents or complicated functions involved.
So we're talking about equations that look like, say, 2x plus 3y equals 7.
Exactly.
That doesn't sound too scary.
They might seem simple, but even linear Diophantine equations can have infinitely many solutions or no solutions at all,
Oh.
depending on the specific values involved.
Okay, so there's still a challenge here. How do we even begin to find those solutions or figure out if they exist?
Well, mathematicians have developed some clever methods.
Okay.
Without getting too technical, there are tools like Bezout's identity and the Chinese remainder theorem that we can use to crack the code of linear Diophantine equations.
Bezout's identity, the Chinese remainder theorem. Okay, those names definitely sound intriguing.
Right.
And I'm guessing these tools help us determine if solutions even exist.
You're exactly right. It's like having a mathematical metal detector to sniff out those elusive whole number solutions.
This is fascinating. We've gone from these ancient puzzles to sophisticated mathematical tools in just one episode.
I know, right?
But we can't just drop those fancy names, Bezout's identity and the Chinese remainder theorem, and run away.
We can't.
We have to at least give our listeners a taste of what they're all about.
Of course.
Let's delve into those tools and see how they help us unravel the mysteries of linear Diophantine equations. And we're back. Okay, before the break, we were talking about some pretty powerful mathematical tools with seriously intriguing names. Bezout's identity and the Chinese remainder theorem.
Yeah.
They sound like something out of a Dan Brown novel.
They really do.
But in this context, though, they act like mathematical treasure maps, helping us navigate the world of linear Diophantine equations.
That's a good way to think about it.
So let's start with Bezout's identity.
Okay.
What's the story there?
It all starts with the greatest common divisor of two numbers.
Okay.
It's the biggest number that divides cleanly into both of them.
Right.
Bezout's identity says that you can always express this greatest common divisor as a sum of multiples of the original two numbers.
So if I'm understanding correctly, it's like a puzzle where you're given the biggest piece and you have to figure out how many of the smaller pieces it takes to build it.
Right.
But instead of puzzle pieces, we're dealing with numbers and their divisors.
That's a great way to put it. For example, let's say our numbers are 15 and 25.
Okay.
Their greatest common divisor is 5.
Right.
Bezout's identity guarantees we can find multiples of 15 and 25 that add up to 5.
Let me think.
Yeah.
2 times 15 is 30, and if we subtract 25, we get 5.
Mm-hmm.
So 2 times 15 plus negative 1 times 25 equals 5.
You got it. Now, how does this help us with linear Diophantine equations?
Right.
Remember, these equations are in the form x plus by equals c.
Right.
Bezout's identity tells us that if c can't be expressed in terms of a and b,
Okay.
that is, if the greatest common divisor of a and b doesn't divide evenly into c,
All right.
then there are no solutions.
So it acts as a gatekeeper of sorts.
Right.
Letting us know early on if we should even bother looking for solutions. What a clever trick.
I know, it's pretty cool.
Okay, what about that other intriguing name you dropped earlier? The Chinese remainder theorem.
Yeah.
What's that all about?
This theorem shines when we deal with systems of linear equations,
Okay.
where we need to find solutions that satisfy multiple equations simultaneously.
So instead of just one equation, we're juggling several at once.
Precisely.
Okay.
And the Chinese remainder theorem comes in handy when these equations involve remainders,
Okay.
the leftovers after division.
Okay.
It's like having different clues about a number hidden within its remainders when divided by different things, and using those clues to piece together the original number.
It sounds almost like detective work.
It really does.
You're piecing together a mystery number from the clues its remainders leave behind.
I love that analogy.
Yeah.
It highlights how these tools aren't just abstract mathematical concepts.
Yeah.
They're problem-solving strategies with very tangible applications.
This is incredible. I'm starting to see why mathematicians are so drawn to number theory.
Yeah.
It's like a puzzle box waiting to be unlocked.
Exactly. There's always a new challenge, a new layer to uncover.
Right.
And even when we have tools to help us, like Bezout's identity and the Chinese remainder theorem,
Right.
there's still a level of elegance and creativity required to apply them effectively.
Speaking of elegance and creativity, you mentioned something before the break about homogeneous equations and parameterization.
Oh, yeah.
It sounds like we're moving from solving individual equations to understanding a bigger picture.
You're picking up on all the right threads.
Okay, good.
Homogeneous equations and parameterization are like taking a step back to see the forest instead of just the trees.
Okay.
We start to see how different solutions are connected, even how to generate infinitely many solutions from just one.
Infinitely many solutions. Now that's a concept I can get behind. Tell me more.
Okay, well, let's start with what makes a Diophantine equation homogeneous.
Okay.
Remember how we talk about the degree of a term in an equation?
Vaguely, remind me.
It's the sum of the exponents of the variables in that term.
Okay.
For example, the term 7 exalius has a degree of 5
Right.
because 2 plus 3 equals 5.
Right.
In a homogeneous equation, all the terms have the same total degree.
So it's all about balance, making sure each term carries the same weight in terms of degree?
Exactly. And it turns out that the solutions to these homogeneous equations, those special whole number combinations, are closely tied to finding points on curves and surfaces where the coordinates can be expressed as fractions.
We're bringing fractions back into the mix.
We are. And here's the really fascinating part. When you have a homogeneous equation, if you can find just one solution with fractions, you can use that solution to generate an infinite number of other solutions also with fractions.
Hold on, wait a minute.
Yeah.
You're saying that one solution with fractions can unlock an infinite number of others. How is that even possible?
It's all thanks to a clever technique called parameterization.
Okay.
Instead of directly solving for our unknowns like x and y, we introduce a new variable, a parameter,
Okay.
and express x and y in terms of that parameter.
Okay.
It's like finding a secret formula that generates solutions.
It sounds like we're creating a blueprint, a set of instructions that allows us to churn out solutions.
Exactly.
Do you have any examples of this in action?
Absolutely. Remember those Pythagorean triples we talked about earlier?
Yeah.
Those sets of whole numbers that satisfy the Pythagorean theorem?
Yeah.
Well, there's a famous formula called Euclid's formula
All right.
that elegantly parameterizes those triples.
So instead of having to hunt for these Pythagorean triples,
Right.
we can just plug numbers into Euclid's formula and they'll just pop right out.
You got it. Euclid's formula gives us a way to generate infinitely many Pythagorean triples, all thanks to parameterization.
This is mind-blowing. We've gone from these seemingly simple equations to exploring their geometric representations, and now we're generating infinite solutions with elegant formulas. This deep dive has taken us on quite a journey.
It really has.
And it really highlights a crucial point about Diophantine equations. Even though we know there's no universal method to solve every single one,
Right.
we keep finding new and ingenious ways to tackle specific types.
We do.
It's a testament to human curiosity and ingenuity.
It really is.
It shows that even in the face of seemingly impossible challenges, there's always more to explore, more to understand. So while we might not be able to solve every Diophantine equation, the journey of exploration and discovery is what makes this area of mathematics so captivating.
You said it.
And who knows what other mathematical mysteries are still out there waiting to be unraveled. Until next time, keep those minds curious and keep diving deep.